Okay.
Okay, right. If I see what I can share on this. Well, first of all, I'll check what files I have open. Um, so it'll be right. I think. Okay, so in the last week or two, I've been looking at sort of getting into the details of Lagrangians and Hamiltonian operators
Mhm.
and things of that sort, and really trying to kind of understand them. Um, so you have the classical Hamiltonian or Lagrangian, where you have the total energy is equal to the kinetic plus or minus the T equals UV. So the kinetic minus the potential and that kind of thing. But so you have the classical waveform then based on these harmonic oscillators, and then if we want to include quantum mechanics, we have to look at the fact that, well, what is it? You're trying to increase the, you have
Yeah,
these
you,
discrete packets of energy essentially that are all
Mhm.
stacked on. It's like the particle in the well scenario, and so you have to add up all of the different energy states, which could be eigenstates, but that might be sort of later on. And then, so all of that needs to be done in such a way that is um, that avoids like maybe ultraviolet catastrophes or something like that. So you have um, you'd have different methods to do that. To do with that, is it Pauli's? No, Planck's work on the just the quantized UV or the spectrum. So where it's what is it again? The quantized waves of the electromagnetic spectrum, which creates a kind of a distribution which is seen in a black body radiation, right?
yeah,
So yeah, anytime you want to chime in and help help out with terminology, please do so, because I'm not
sure.
I haven't been thinking about this all day or anything or all week, so I'm kind of winging it here a little bit. So, but it gets started. So you think you're doing a Lagrangian for a nice sine wave, and you think you're getting somewhere, but then you need to include all of these different energy states, let's say, and then you need to renormalize it, and before you know it, you don't know where you are. You don't
Mhm.
really have a result, and even then you're only working with massless particles, and even then you're still, you need to bring the Dirac equation if you want to do high energy physics. And so there's a lot of, how would you say, I want to say there's a lot of ins and outs, but there's a lot of facets to the
Mhm.
to the problem. Obviously it's a complicated issue. So so basically, how do we go about, maybe, well, to begin with, I was just trying to graph these things to understand them, and so that I could maybe incorporate them into my work at a later point. Um, and I think one of the big issues was, well, I was actually watching a video by, I think it's on Theories of Everything, which is
Mhm.
that channel by a guy called Kurt J. Mungle, who I've shown you his work before, and he was interviewing Peter Voigt. Now I don't
Mhm.
know if we can go ahead and we could watch some of that, maybe, if you haven't seen it.
Yeah, highlights. Yeah, we can do the highlights.
Okay, um, because it was really interesting. Uh, I wonder, can I just?
Yeah.
I'll search it up here, see if I can find it. Uh, okay, so I'm just going to type it in here. Theories of Everything. It's Kurt J. Mungle and Peter Voigt. Great. That was kind of one of his most recent, their most recent talk. So it should come up. Oh. All right, he did one with podcasts, maybe. I don't know. Sorry. I thought it was very recent. Maybe it wasn't. Forgotten geometry, a new path to unification. Yeah, that's probably it. Oh, that's only 20. Oh no, that's an ad. Right. Okay, we have to look at the ads. I'm not fully on board with that. All right, so we'll just talk about it anyway then, because we're not gonna play the video. But so what he was talking about was you have these. You know the way a lot of my work has been based on these gauge groups like SU2, SU3, and U1 kind of. But particularly SU2 because of how it works together with SL2Z and SL2C, and those matrices then play a role in general relativity through the Lorentz group and Poincare group and all of those. And so then you have these matrices from general relativity, and then you have the ones from quantum mechanics, which are the Pauli matrices, and those two are linked. You know, the SU2 and SL2C are connected. So that is the kind of idea towards a unifying principle, which forms the basis then of quantum field theory, essentially. So when you're using these, you know, I was thinking of the SU2 or U1 as being a gauge group. So like in U1, it's just a circle, which becomes then a wave, a sine wave, which is a harmonic oscillator, which has potential and kinetic energy. And then you can figure out the total energy of the wave function of a classical, you know, harmonic oscillator to begin with, and then so on for the more complicated cases. And so that's kind of what I was trying to, because you often see like a lot of differentiation signs besides the wave functions, and then you have the gamma matrices in there, which contain the SU2 groups, and so it seemed obvious to me then that I should begin to differentiate the gauge groups in order. Because of Emmy-Noether's theorem, isn't it, that with these spin operators, the U1, it's like energy is conserved within that gauge group. So as it goes around, as the sine wave goes up and down, the total energy is zero, essentially. Seems to be the case, you know. So because the kinetic energy and the potential energy are equivalent to one another, something like that. So then you could take it up to a higher level with SU2 then and say, well, let's figure out the actual rotation of the SU2 wave and make sure that that is also zero, and so on for SU3. But then I was thinking, well, maybe there's not much point in doing that, because another thing is then the aspect that Voigt brought up was that, you know, how if you start increasing the energy of these particles, so in the U1 group, so for the electromagnetic force, for the weak force, and for the strong force, and you bring it up to higher and higher energies. I think it's like 10 to the 15th or 17th GeV, something like that, or maybe it's 10 to the 17th something. Anyway, I'm pretty sure it's GeV, but so a lot, you know, it's very high energy, so very high temperatures, and they all sort of converge at a certain point, but they don't converge perfectly. They kind of miss each other. But that in that area then is considered to be the unification of all of those three forces. So they have to unify at that energy scale. But if you were to change the gauge group so that they all fit into like something like SU5, then you can close that gap so that they will kind of, in fact, close it. You have to go higher. I think they go into like U1000 and all of these other crazy groups, and you can get them to all to just all cross at the required energy. But I mean, presumably you could get them to cross anywhere, you know, because you're just changing the groups to get the thing that you want it to be, because it isn't that thing at the moment. Like, yeah, when you just do the equations, that there is no perfect unification. So I'm not entirely sure what they're doing there. It also raises another bit of a question, which I'm sure has like a very, well, I'm sure there's a rational answer to this question that I'm just not aware of. But let's say we increase the energy of a particle. So if we increase the energy, it's supposed to increase its mass. Yes, so mass times energy. But if we increase the energy of the particle, well, okay, I might have already solved this thing just by talking about it. But you increase the energy, you increase the temperature of the system, right? So if we say that the three forces are unified at a particular temperature, which is 10 to the 15 GeV or something, then that's a very high temperature. Okay, so the temperature's gone up, the energy of the system's gone up, therefore the mass of the particles has also gone up. But you know, so I was thinking, well, like, wouldn't that mean that if we just heat, like if you have a block of metal and you heat it up, then the temperature's gone up, so shouldn't the mass also go up? But obviously that doesn't happen. But I suppose the difference is that temperature is a kind of a global phenomenon, like emergent from all of the interactions of the particles, whereas the particles themselves, you know, would have more energy, and therefore should have more mass. But maybe it's like a different kind of, you know, I think there's different types of masses as well, inertial and other ones. Can't remember them all, but
I think there is a.
So, yeah. Do you want to just discuss that a bit?
Yeah. I mean, I think there is a temperature cutoff because mesoscopic level, when you are heating material, it doesn't affect the atom, the subatomic particles. You know, it's only the outer electrons and things like that moving around.
Oh, okay. I didn't know that.
So, yeah. So it doesn't affect the...
Don't they kind of vibrate, though? Don't they begin to, like, if you were to heat something up, like, to the point where all of the atoms break apart and
yeah, it's much higher temperature. So, right. Yeah. So we are talking about different states of matter, right? We go from the solid, liquid, gas, then plasma. When we go to plasma, like in sun, in the stars, it's plasmatic, right? So they're ionized. So then it starts having these quantum effects, right? I mean, the subatomic particles start splitting up.
We're up here at like 10 to the 15 GeV.
Yeah, so it's much higher.
Yeah. This is like beginning of the universe type energies. Like,
yeah,
it went back when all of those three forces were unified.
Yeah.
So presumably, I mean, maybe that would affect the masses, or maybe not. But anyway, it was just a kind of a passing sort of curiosity I had when thinking about it. But I mean, you know, I'm sure there's lots of crazy considerations to be had, especially at the early universe, and where a lot of these you know, laws of physics break down as well. So I'm not too concerned about it or anything. But the bigger issue, bigger concern that I had then was, well, maybe I'm going about the whole gauge group thing the wrong way. I'm thinking about it one way, and that's fine. But it seems like, you know, in order to prove your grand unified theory or your theory of everything, you need to get in there and start calculating these energies to see like where they all cross. and to unify them at some sort of temperature. And I looked into the mathematics behind that, and I found it like very difficult and confusing. And I don't even really see the gauge groups in there. So I'm wondering, are they actually, maybe they're not even using the gauge groups. Maybe they're just saying, well, we know that the electromagnetic scale or force is the U1 gauge group. So then they just take the knowledge they have about the force, and they just increase the energy to get their plot. And then they say, and then they do the same thing with the weak force, and the same thing with the strong force. And then they call those U1, SU2, SU3, but the groups aren't actually really there. That's possible because, well, I couldn't really see them in there. I mean, you know, they're in there because they're just part of the forces. But so you can go the opposite way as well, and then say, well, okay, well, you have your complicated, you know, and useful and important analytical tools, which are mathematical and very descriptive using constants and stuff like that. But then you also have the gauge groups. And if we're separating them, then you can just look at the forces from the gauge groups as well, without necessarily going into the details over there of the other things that we were talking about, constants and all of that. So that's what I think I've been doing. I've been more just focusing on these gauge groups without necessarily applying them to like specific problems maybe that might come up. And so, you know, I was concerned, like, because if you're working on something for a long time and then you discover, oh, well, maybe I'm just uneducated in this field to the point where, you know, to the point where I really didn't know what I was talking about. Like the depth of complexity here is so big that you'd want to be studying this subject, you know, at an undergrad level, and then on and on to get get a real good handle on everything. And so that's what I was trying to do by going back to the classical Lagrangian, and build up and get closer and closer to this quantum sort of thing where I can actually manipulate the Lagrangians and start, you know, start calculating some of these things like the masses and bringing in the constants, so that I'm not just and bringing in the gauge groups, so that I'm not just working with gauge groups by themselves kind of thing. But then actually later on, I watched another and even more recent interview that Kurt J. Mungle also did. This time with a guy called Garrett Lisi, and his theory of everything, which is like based on E8, but specifically the talk he gave was on triality. And it was pretty interesting, but what I got the sense was, like, again, he would have gone to I don't know if he did a PhD, but he probably did, but he didn't go into academia, but he's definitely very well up on a lot of these things to do with, well, he's well up on gauge groups. He has some good mathematical background, but he wouldn't be like, you know, really far out there. But he would have a lot of physics knowledge, so to do with charge, time, parity, classical physics, general relativity. I think that's really where he's coming from, and also then some of the quantum aspects. Like he says, it's just a general relativity theory, but really he's bringing in a lot of the quantum stuff as well. So I'm not entirely sure why he's saying that, but yeah. And so the point I'm trying to get at is he starts then bringing in other complicated issues to do with the Poincare group or the Lorentz groups, SL2C transforms, and general relativity. So that side of things, and charge, time parity, CPT violations, and then he's like plotting the Dirac spinors on these graphs, where the axes of the graphs are like time and parity and charge, And so you have like this charge space and this parity space and whatever. So it's interesting, but once again, it's like the other side to. So we talked about the vagaries and the difficulties of quantum mechanics. Now we're moving into the similar thing for general relativity, which is another thing that you'd want to do an entire course on to really understand, I'd imagine, the difficulties in that process. And so we're trying to get these two things that are very difficult and to get a handle on, from a I guess phenomenological point of view and a mathematical point of view, and join them together, even though we don't really know what we're talking about. So, or I'm just speaking for myself here. But then the more I was listening to him talk, I kind of felt like, in some sense, okay, so here's my analogy is, if someone is, like, let's say you're looking at your computer screen here and you can see the menus at the top and other buttons around the place. And you can easily go into any of those menus and like open up a program or open up some files and folders and no problem. But if I asked you to crack open your computer and open up the CPU and tell me, what those registers do and which, you'd have a much harder time. And I think most people on the planet would. And so I feel like, in some respect, you can get like these amazing quantum physicists and general relativity people. They're like the people who are cracking open the computer, or they're not even cracking up. They're building it from the bare metal up, and then you can write. They're also writing probably the software for the OS that we use. And, but the point is that I'm trying to make there, I think they're very focused on the minutiae and the technicalities. And they may have, and this is just a guess, they may have overlooked the fact that once you get to a high enough level, you can kind of start working just with things on a very superficial level, possibly. And so like we do with the computer on a day-to-day basis. So I think that's what I'm doing. I'm sort of surfing over the surface of a lot of complicated stuff by just making sure everything is very simple. Now, having said that, I wouldn't call the work that I'm doing simple, but I think it's like we have a lot of complexity at the beginning. They simplify it down to these nice little groups. So the entire standard model just becomes U1 times SU2 times SU2 times SU3. So that's incredibly simple. And then from that, then we begin to make it more complicated again, but only because, that's needed, because we can't just end on that simple equation that I just said. It doesn't tell anyone anything. So we need to start expanding that to make it more explicit, basically. And I think making things explicit is very difficult in mathematics, especially when there's a lot of terms. And you'll see that often with mathematicians. They'll prove something.
Yeah.
Let's say they'll prove, excuse me, they'll prove that, I don't know, that, what's that thing called?
Theorem or something?
Right. Well, let me think. No, let's say they'll prove that there's 10 600 cells in a 120 cell. Okay, so mathematically speaking, they know that you can fit, if you get a 600 cell, you can fit it into a 120 cell in 10 different ways with different reflections. But they probably won't sit down and figure out what are the vertices in the 120 cell which reflect all of those 600 cells, because in their mind they're thinking, well, who cares? Who wants to read through all these vertices, Well, like, I definitely would care. Like, I would want that information. But for them, I think it's enough to just prove it, lemma, blah, 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 and then proof. And it's like 3 lines of code, like or not code, but maths, like 3 equations, something like that. They want to do everything as quickly as possible, but not explicitly so. So yeah, so I think that that's good up to a point, but if you really want to solve this problem, you need to be explicit. You need to say, you know, at least there might be 12 ways of doing something because of all the symmetries, but you just select one and explicitly state, well, this is one possible way that this works. And that's what I'm trying to do by assigning all the particles to the vertices in the 600 cell, for example. I think there's like 12 ways of doing that, or like assign them all to the 24 cell. There's definitely 12 ways to do that. And then assign those to the 600 cell, and then keep going and keep assigning, and then find what we're looking for. Interestingly enough, actually, Garrett Lisi ended his entire talk on the 24 cell, and yeah, he had some interesting points that he made on that, because the 24 cell obviously is 24 vertices, which is 3 times 8. And he was saying that it's made up of 3 4-dimensional cubes, which, you know, I was thinking, and I think Kurt J. Mungle, the interviewer, thought as well, that what he meant was 3 tesseracts, because 4-dimensional cubes sounds like a tesseract. But a tesseract has 16 vertices, I think. So if you have 3 of them, that's a lot more than 24. So he was like, no, I mean like 3 cubes that are in the 4th dimension, or you know, so they're just normal 3-dimensional cubes, but that live in the 4th dimension. But I don't think he's right about, I mean, he might be correct on that, but well, my understanding is that there's 3 16 cells, which are basically 4-dimensional tetrahedrons. And so there's 3 of those in a 24 cell. But so the final point he was trying to make was, and he didn't make this from a mathematical point of view, he didn't have a mathematical proof. He was just looking at his CPT diagrams and the way the Dirac spinner, he took like one Dirac spinner and then he was able to transform it somehow. It wasn't very clear what he was doing, but ultimately he got all of these, he got 24 copies of it, and then he was somehow able to then say that, okay, because there's these 3 groups of 8 particles in a 24 cell, and he was describing these each to 3 different cubes, which are really 16 cells in the 24 cell. And then he was saying, oh, because of my axes, space-time axes or whatever, which actually I don't see how they transform over, because excuse me, he keeps switching between you know, Euclidean space, 4-dimensional Euclidean space to Minkowski space and back again, but he's not actually showing you how he's switching between them. And then he points out that they have no way to switch between them, that this hasn't been figured out. And Kurt J. Mungle says, oh, well, have you looked into Peter Voigt's work where he's trying to use the Wick rotations, which is really just like multiplying by minus I or multiplying by I or something to change the -1 into a +1, which is great and all, but I don't think that's going to cut it. And then the Wick rotations also has further stuff to do with temperature and the Boltzmann constant and that kind of thing. So like I said, a lot of this stuff gets a bit complicated and a bit confusing. And I think that people are confused. Like the reason why everything looks so complicated and difficult isn't just because it's complicated and difficult. It's because the people writing this stuff, I don't think they fully understand what they're talking about. I don't see how anyone could fully understand this stuff, because I think it's just very weird and complicated. Not to say that the answer isn't going to be understandable, and also not to say that everything's simple, you know, and that it's all just going to be like ABC when we figure it out. I don't believe that either. But yeah, so I'm not entirely sure what I'm trying to say there, but I think you understand a little bit, maybe. So yeah, so he's talking about this thing that's obviously a 4D Euclidean object, and then he's saying that thing it tells us based on mathematics that there must be 3 different time-space dimensions all over. So 3 different universes, essentially, each with their own time and X, Y, and Z axes that are different to each other somehow, and that the 3 generations of particles, so let's say that the electron, the muon, and the tau, each of them live in these different universes, but that all those universes overlap on top of each other. And I'm not saying that he's wrong or anything. He probably is right. But I just thought it was a bit strange because he kind of switched from a Minkowski thing back to a. But I suppose somehow, sorry, I've got a bit of a sore throat. Somehow he's able to take some of the elements from Minkowski space, namely the time, and bring it over to the Euclidean dimension. So maybe that's how he's making that call. So yeah. Anyway, I hope that was. I decided not to show any code this time around while I spoke because it would have just been distracting and totally pointless anyway, because I didn't get too deep into the code on the Lagrangian or any of the you know, it wouldn't have been groundbreaking work. We'd be going back to the early 20th century kind of thing, which is, you know, fine, but just not. So that was kind of my my exploration on that side of the complicated vagaries of the mathematics, and how, you know, and just trying to make sure that what I'm doing has some sort of valid sort of foundation, you know, that I'm not just fooling myself, you know, or everyone else or something. I'm sure I wouldn't be able to fool these people, but like, it's not my intention to. Because, you know, the worst thing would be to publish something, and then people go, oh, this is all wrong, or, you know, to make a big. It's perfectly fine to send your work to be published in a journal and have the reviewers tell you it's wrong, because then that's good, or for them to miss it maybe and to have it published, and then someone to come back and say, oh, this is wrong. But I think what would be bad would, let's say, to be in a position where maybe, I'm just trying to think of an example, but maybe Eric Weinstein or whatever, where he published, and he never published it in a journal, I don't think. He published it on April 1st, so April Fool's Day, his theory of geometric unity. And it got taken apart by, you know, someone, and I think that's fine, because that's the way science works. But he refused to listen to any criticism of his paper because one of the authors was anonymous. So yeah, so something like that might be embarrassing just because it gets blown out of proportion. But I think the main thing is, like, if you were to come out and state publicly, and, you know, in a very public way, like he's doing, because he's obviously very famous, and saying, I figured it all out, and then to have someone say, actually no. But at least where he's coming from, like a lot of the foundations of the mathematics are probably correct. I mean, one of the big issues of his work is that he cannot remember what this operator is that does this particular transformation, which is the crux of the entire theory. And it's been so long since he left university that when he was working on this, he went off to do other things in the business world. Then he comes back to publish this, and then he admits, I cannot remember the operator that does this transformation. And so it's unverifiable, so it just becomes a bit of an embarrassment then. But that's a different kind of embarrassment. Whereas I think, like, if I was to, like, present myself as some sort of expert in the realm of quantum mechanics, which I'm obviously not, as I've just demonstrated, or general relativity, which I'm obviously not. So then you're saying, oh, well, here's a theory of everything based on all of these gauge groups, and you don't even really fully understand what's going on in the mathematics behind that. then I think that would be embarrassing. So my aim was to try and mitigate this issue as quickly as possible, and that's what I attempted to do. But I don't know. So either I'm convincing myself that everything's fine and I can just continue on, or I'm fooling myself. So yeah. Anyway, I think I rambled enough there. Do you have any other points you'd like to make?
Yeah, one of the things recently I found that what's the math and the physics. So I think I like the tensor thing. For example, you take a case of, I was teaching recently, I think middle school students, last week about the math. Suddenly dawned upon, because they don't know what algebra, they're getting the thing. You have X and then you have a number, and then you do that. So I said that that's like a box. X is like a box. You don't know what's inside the box. So it can have many different things, whereas the number has specific value. So I was thinking about then, in the similar line, I was thinking about what is that differentiates, like in the case of Schrodinger cat, or you look at something, the double slit, and that changes the waveform. What is the one that's behind it? And I think my tensor thing may help in tensor gradation. So yeah, when you are looking something from a distance, it's like a tensor. You don't know what is it, right? So when you come there, you open the box, the tensor degradation occurs. Now, very important thing. I think I had to do the math, but I think this is the important thing. We think it's scalar. Actually, it's not scalar. It's only rank 1. We reduce to rank 1. So, for example, simple thing, measurement, right? Ruler. So, ruler, you have one point, the other point, and there is a distance. So, it's actually a vector. So, like what you call the measuring rod, like Einstein is talking about in the general relativity, measuring rod, and then he talks into light years and things like that. But that's actually a vector. It's not scalar. Very important. That's I'm pointing out. And also the time is actually a vector, because we are going clockwise. We cannot go anti-clockwise. The time goes forward. So suppose I didn't bring it. I want to show that in some other thing, that if you have like a tape, right? Tape measurement, and then you pull out, you can have a clock inside. Clock that tells how fast it's moving, how fast that, suppose you are measuring something.
Yeah.
Okay, that will help, because everything is a vector, it's not scalar. So all the tensor, like I said, the time is a tensor, the future is like a tensor, but it degrades into rank 1 tensor, which is a vector. And now the vector is the one that is seeing the direction. So you never get a complete scalar. Okay.
Yeah, well, that's what I've been saying. I've been trying to say that to you for months.
Okay.
Yeah, anyway, that's fine.
Yeah.
That's good that you're
thinking in a different way. Yeah.
Yeah, because
math.
To be honest with you, I've been trying to tell you that for a while, and then I just gave up. And then I was just you were talking about turning it into scalar time, and I was like, okay. I was just like, why not? Maybe it's a good idea, and now you seem to have gone over to the vector side of things. So yeah that's good, because I think potentially you could do more with the vector. But that doesn't mean, I think, like, if you were to turn it into a scalar value at some point, then it would be like, all right, well, time is stopped because there's no direction. So it still could be useful if you can bring it to a scalar, but maybe for general relativity or something where time stops. So it just gives you more to work with, I think, Rajan.
Yeah, and I think this is a very important concept. I think this is where the scientists are getting confused, like you said.
Right.
And the important thing is like math, right? Is math a complete scalar, right? You are putting in a balance, right? It's very important. The physics is important, the measurements and all that. I think it's worthwhile thinking more deeply into this. So you're putting in a mass, right? Is it a real scalar or is it also a vector in some sense? So that's something we have to think. Right now we think it's a scalar. If we just measure the, but actually, it could be a scale. It could be a vector because we think it's a gravitational interaction, right? The gravity is pulling in.
Yeah.
But that's weight. That's weight. So weight is definitely a vector, whereas mass may be scalar. I don't know. I'll put quote unquote. I'm not sure.
Well, that's something you can examine. You can make it a dimensionless quantity, can't you?
Yeah.
Which has to be a scalar then, right?
Yeah. So like I say, I think the previous ones I have shown you. I think the previous videos. I don't know whether I need to pull up, but I have it there. But I say that everything is like a signal we get, like outer space, wherever, right? But the signal is so large, we have to uniterize it. We have to do signal to noise ratio so that the instruments can measure it. So that's essentially what we are getting, like your cosmic microwave background, gravitation waves, it's all signals, right? So signal to noise ratio is the one. The other axis is like the coordinate axis. It's like your physical chemistry where you say order of the reaction and a coordinate, that makes a lot of sense. I used to ask, why is it that? But it makes a lot of deep sense. Why is it? Because what is that code? So now we think that code is space and time, right? Space and time. But the space itself is not one dimension, like you have shown. X to the power n, where n could be like your 4 that you are shown. And time also is not one dimensional, t to the power m, but the dimension is a virtual dimension. So it's like a rank of the tensor is probably 6. So x to the power 4 and t to the power 6 is a specific type of solution. That's what we should use to analyze this spectrum, which has breaks. Like you said, with a Tumbo, it breaks up, things like that, because you are connecting the photon and the phonon coming together. In the cosmic background is probably more photonic, whereas gravitational wave is more phononic in some sense. So transverse and the longitudinal and the transverse waves kind of thing. It breaks down into that. So I'm going to do the fundamentals of these. I think it starts making sense. And where the string theory went wrong, that's something I am keeping in the back of my mind.
Yeah.
I think I have some idea because that's the most beautiful math theory, right? I also emphasize in my history.
Well, they do say that, but sorry to interrupt there, but
go ahead.
Just I think it might have been again in one of these two interviews that I watched, either the Peter Voigt one. I think it might have been the Peter Voigt. No, actually, I think it was Gary Lisi. He just made the point that one of them anyway made the point that again, like, good idea or a simple enough concept really at the start of it, but gets so complicated, especially as it goes along. It just gets incredibly complicated. And I wonder again whether they know what they're, I don't think they really, well, I would think that they would admit that they don't know what they're talking about. But, I'm just wondering, well, okay, so that could be true of something that's like highly theoretical, that's very like fringe in the sense that it's like on the edge of what's being discovered. But in general, we would normally not project that onto well, I suppose you could say that maybe Wick rotations or something isn't like, it's not canon or well, Voigt said usually when he's dealing with stuff, it's very obvious what's happening, and everything's well understood and it's clear. But when he said that when you get to this Wick rotation thing, at that point, things weren't clear. So again, that could be like a leading edge. Like, that's an indication that more work needs to be done in that area. And so he's working with Wick rotations for some reason. Oh yeah, I think he just says his point is, look, the universe is 4-dimensional. but you can turn time into a spatial dimension to work on problems and then turn it back, which is kind of what I've been doing. But I'm using a different method which doesn't involve Wick rotations, but involves the 600 cell and the 120 cell. So, but I haven't written that up yet. But I don't know how they'd respond to it. But clearly, those two are the people to talk to, and everyone else, as far as I know, is either, well, they're just not around. You know, I don't know who they are. So there's two people. Well, I mean, there's other people that are, I guess, connected to them professionally as well. But these two seem to be particularly Voight seems to be the one that's most interested in this question, at least most vocal about it. So be interesting to see what he thinks about it. But because he has his own pet theory and his own, he's probably the last person that wants to hear a different theory, you know? He'd be like, yeah, I want to know. Anyway, so it's interesting what you said there about signal to noise ratios. I've been trying to apply it to some of the work that I've been doing, but I'm having a very hard time downloading the data that I need to do it. Whenever I try and download it, it comes out in some kind of it's just not in the right form. So I suppose but and also I'm probably using the wrong method in terms of how to generate the signal to noise ratio. But my method is to, well, I get the data from the swarm satellites, geomagnetic data. Now there's an error here. Mode. URL open. Okay. I'm just going to run that again. See if what happens. Okay, there's still an error. So, well, then I get, okay, so I get the different data. I get seismic data. And I plot all of that. Then I resample it as frequency days. I sort the index. And then I do something called a seasonal. So I do a seasonal decompose, yeah? So we decompose into trend, season, and then residual, which I'm taking to be the noise. And then I do a signal to noise ratio equation where I take the maximum of the signal divided by basically the average of the noise, and then I get a value in this case which is minus 13,757. Now, when you go on to the Wikipedia page about signal noise ratios, you know, it's similar to what you said, where it needs to be a value of, I think it was, it needs to be 1-to-1 or something.
Yeah, I think the maximum should be 1. It's like probability function.
So, right. So it says it here: a ratio higher than 1-to-1, greater than 0 decibels, indicates more signal than noise. So presumably, then, if it was what 2-to-1, or right, that would be again more signal than noise. But if it was, see, I'm not entirely sure what they mean by that. But okay, so one definition of signal. So I should know what they mean by that. But sometimes these very rudimentary things, kind of, the meaning of them passes me by because they're so simple that they're never explained. Kind of. One definition of signal to noise ratio is the ratio of the power of the signal, meaningful input, to the power of background noise, meaningless or unwanted input. So SNR equals P signal divided by P noise, where P is the average power. Okay, so that is interesting. So there is an average in there. But then the power sounds like the maximum, doesn't it? Because it's like, but it doesn't necessarily need to be that, because power is defined in so many different ways, especially in physics, isn't it? It's like,
yeah,
does it work over time or something like that?
Yeah.
But then power in a signals setting would be different. The unit of power is a watt. You know, so what are they talking about when they say power? Presumably it's a signal, you know.
So you have the frequency, then you can convert the frequency to energy, and the rate of the energy would be the power. The time rate of the energy will be the power. So
okay.
So higher signals, higher frequency signals will have higher power in some sense.
Right. Yeah, that makes sense. Okay, so the ratio of the power of a signal. So when we're saying the maximum power, well, yeah. So anyway, so the equations that I'm seeing here are very different to what I employed in my particular case. So not sure why that is. I had this app that lets you listen to different infrasound signals, and in the sort of documentation that came along with the app, they mentioned signal to noise ratios, and they gave that exact equation that I just mentioned. And like I say, anyway, so getting back to it, the results that I got was like minus 13,000 or something like that. Yeah. So, I mean, what is that in terms of a ratio? I suppose that's the answer to the ratio. You'd need to know what the original sum was in order to know. But presumably, because it's minus, sounds like it's less than 1 or something. So, who knows why it's a minus thing? Maybe it's minus because of the data being used, and we should use an absolute value, because I don't think you can have minus decibels, you know.
Yeah.
A signal to noise ratio can be
maybe the noise is written as a negative value. So your signal to noise becomes negative.
Oh, okay. So you're saying that there's a lot more noise in the signal because it's negative.
Yeah, negative.
Okay, that makes sense. I would say
below that, suppose you have an axis here, x-axis. So
yeah.
Above that is a signal, below that is a noise. So they'll treat this as a negative thing. I don't know whether it's correct, but that may be the reason.
That does sound like it, because I would have expected there to be a lot of noise in this signal anyway. So signal to noise ratio with the so the previous one that I mentioned was the signal to noise in the seismic activity, which is obviously going to be very noisy, right? And then in the geomagnetic anomaly activity, or just actually it wasn't even the anomaly, it's just the geomagnetic activity for the same period of time, you get minus 1757. So both of them are very noisy, and they're both natural phenomenon, and it's also a very chaotic situation. So we'd expect a lot of noise. So yeah, I mean, that was just a fun little. I just wanted to attempt that to see if I could get any results that were kind of conclusive, but I just wasn't able to interpret it. But yeah, I think that sounds okay to me. Because I think a lot of what this Wikipedia page is talking about is more. I mean, it goes into noise and grayscale photography, signal to noise ratios. So I think it's maybe a slightly different area. Whereas if you're using like maybe a pure signal, like a univariate kind of type signal time series, maybe you don't have to go into all of those complicated work. And yeah, so I think that's it on that front then, because I can't actually. I'm not, so by the sense of it, I'm not going to test out any different equations on that. We'll just leave it, because in the end, if it's saying the signal's very noisy, you know, it was more. I think it was more just like the challenge to see if I could get a proper result. So I'm happy enough with that.
Yeah, suppose you have a big signal like that. So I think they'll make a cutoff. Okay, this much is noise. I cannot measure that. So noise. So the one below negative. So the one above is a signal. That's very small compared to this. It's a negative. So there is too much noise, like you said, in many cases. I think that may be true of the dark matter activity. If I'm thinking about it, the superluminal thing may be very noisy that we cannot measure it. That may be where it becomes dark matter because it doesn't show up. Dark photon and things like that they're talking about now, the manual and all.
Oh yeah.
So that's an interesting aspect that actually, we have everywhere this noise somehow, I even call it nuclear noise sometimes, but everywhere there is noise, but something happens and then the distorted field and then creates a signal. That's what I'm saying. So that signal is what we are. And then I analyze in terms of matrix, entity, vacuum, and quanta. We are quanta, where we have both matrix and the entity. So I like the brain theory, the M theory and the brain aspect come into the picture. So the matrix, everything kind of goes into the matrix. Everything kind of spreads out and dilutes, in the universe matrix. But the entity is a local phenomena, and gravity may be something like that, a graviton or something that's happening. So it's like nucleation, like you mentioned. Now I thinking back, I think we'll pick up on your idea of a tempo, which then with the discretization, your discretization of these signal. So you have a specific thing. That discretization may be the fundamental nature of universe itself. The universe may be homogeneous, so let's say noisy. But what discriminates is this slight variation.
Well, it suggests to me, Rajan, like we're talking about, just as you're talking about it there, it just occurred to me. Well, if we're dealing with this signal, which is like a discrete thing, which is like an MP3 signal, which is a digitized thing, and of course MP3 then is, well, so we have a digitized signal to begin with, and then we have MP3, which is sort of also digitized, but it's like a data compression algorithm. So in some sense, yeah, if you get this work, you might be able to get some sort of data compression algorithm that shows that the universe compresses data. So, so a bit like how Emery says, like, oh, there's only one particle, and for that particle, it's the only particle that exists or whatever. I mean, that's the ultimate data compression, isn't it? Because
yes,
like, the entire universe is now just a single particle. It's pretty interesting. So,
yeah, actually, they talk about the wave function in terms of entropy. There's only one value for that, minus k ln of omega, whatever that value is.
Oh, right.
Yeah, there's only one value for the universe. So
yeah, whether that's
all of them.
Whether that's accurate now, though, because I mean, attempting to apply those the what are they called again? Thermodynamic equations to the universe, or it's a fraught activity, but it's obviously it has some potential legs, doesn't it? Because I mean, you can do the same weirdness with this Wick rotation, where you think you're just rotating from a four-dimensional Euclidean space into a Minkowski space, but for some reason the inverse temperature and the Boltzmann constant's in there, and it's like, well, what's that doing there? It's a bit strange. So again, go ahead.
Actually, I was trying to solve the problem. One of them is the math is tricky. I don't know whether I can show. I may have shown this, but like you said, no one pull up that. Let me see. I don't know whether I can pull up that. So if I look at here, think I had shown this before, but I think I have to do the math completely. But this is what I was talking about earlier, and as you know, the previous thing, the signal and the signal to noise ratio and all that. But this is a coordinate axis. We think it is space and time. That makes sense. Okay. So this is the fundamental, most fundamental. We start with a signal to noise ratio that we measured, and just a code. What that code is the key thing. And we, I think we probably believe that it is the space x to the power m and t to the power m, x to the power n and t to the power m, and this is rank of the tensor. And when you differentiate, it's like getting your tangent plane type of thing. You get this one. So this may be cosmic microwave background, and this may be gravitational wave. So I can find that. So when I try to solve that thermodynamically, oh, this is kind of a little nuts, but I have to rewrite this. But see, I get the thing, and then you have the.
I can't really see all of that. We can't see that, Rajan. If you could move it more into the camera.
Is it now? Can you see?
Yeah, I can see a bit more. It's kind of a bit you know, it's not aligned with the camera. It's a bit the camera's straight and it's more at an angle. Yeah, if you move it the other angle, rotate. Yeah, that's getting better. Better. Yeah, it's a lot better. And just make sure it's all in frame then, you know, because it's drifting a bit to the left. Yeah.
How about it now?
A bit more to the right, shouldn't it go? Yeah. That's looking good now. So what have you got? Magnetometry, Motify, on graph. Right. Okay, so you have this sum. What is that? The sum of f with this 4 vector or 5 vector.
Yeah. Vector, so you have the regular, like a Fourier or a sinusoidal thing, right? Regular thing, or a broken thing that I showed you before. I cannot show here, but the discontinuous wave.
Oh, right. Yeah.
And then I add this thing.
Yeah.
Which is the one. So I have this regular thing. This is the regular thing, right? That's a sigma m. The math of that, and then I add this one, right? Add this gravitation wave, which is modulation or a distortion of that. So I add these two things together, so I get this math. And then the interesting thing, I try to solve the problem. You know, this math is little complicated, but I think I can justify that. I think that's one of the things people had problem with. When you try to solve this problem, you have to look at this particular solution. And the particular solution, eventually, I can convert this to temperature. And the interesting thing, interesting thing here is that the temperature, I have to rewrite this one, but I can show on one end it is a vacuum. That is, I get a value sigma. When you get absolute value T to absolute temperature, then this value of the signal goes to 1, signal to noise ratio. So that's superconductivity. Okay.
Oh, cool.
When temperature go to infinity, you get vacuum. So the two ends of the world are universe are, one is vacuum, the other one is superconductivity. So
sorry, say that again. The two ends of the universe. One is superconductivity. The other is vacuum.
Vacuum. Yeah.
Oh, right. That sounds really interesting, Rajan.
Yeah. Yeah. So that's I have to do the.
That's really good work. If you can write that up and obviously get someone, you know, other than me to look at the maths, because not that I'd be totally hopeless, but I'd say somebody with But by the sounds of it, you know, it's
peer review. I'll send for peer review.
Yeah, absolutely. I'd say that's once you get it written up, and I'd like to read it.
Yeah,
and then by the sounds of it, that could be, you know, you could send that to a good idea to send that to a proper journal to see.
Yeah.
Get original. You know, get someone to look over it that you trust from a proper journal, I guess. So.
Yeah, many of the journals, you know, they have, although they may not be the top journal like the physical review, these people are really good. Some of them are really outstanding. It's even probably better than physical review, I would think. Physical review is more there. If you don't have general relativity and quantum mechanics, they don't even look at it.
I think there is some issue though with some of these papers, some of these journals.
Yeah, like, true. That's true.
You can give your work and then they own the copyright to it and stuff like that.
No, many of the things, because I established some things, I think, you know, I think they have not cheated me so far or anything like that.
No,
they published it, but you never know. Really good thing like this, you know, you have to be very careful. But that's why I'm putting it here, so that we can show this is like a copyright YouTube, right? So which means that I have talked about it. We can always contest that, but I don't want to go in that direction. Of course, that's a very bad thing. But I'm saying that, you know, I think they were, you know, they do such a way, many of the journals, I don't know, they can continue doing that really they are holding a line so that the reviewers cannot get away with it, you know. So they're giving you benefit of doubt, and they are kind of, you know, intermediate that recognize that you have done this one, and then they're looking for the review just to justify that. And some of the reviewers, really, I'm impressed with the Schrodinger equation, things like that. And the comments they give are not unnecessary comments. They give very small, but they're to the point, and it's very helpful. So I think, you know, I really like those things. Previously, they don't even accept in dark universe, other things, other places. But also, you know, they didn't reject it. They didn't reject it. You know, the surprising thing is
papers or some of these journals are just money kind of, you know, they want your money to pay for the
I mean, the physics essays we are starting, you know, we are paying much higher, but the reviews are good. But many other things they give some discount, so it's not too bad. But again, you know, like Oriental Journal is free. It doesn't they don't charge anything, and sometimes they have good reviewers.
Which journal is free?
Oriental Journal of Physical Science, or JPS. But sometimes they have good reviewers.
More about the standard of reviewer there. Sometimes I'd say it's probably pretty good, but
yeah. Sometimes they are good. Sometimes, you know, they are outstanding, like how we did, and they did good comments on that, and they had to, and some other things I send later on also. But at times they are a little shaky. It depends on the reviewer, I think. They use all kinds of reviewers.
Yeah.
But some other reviewers are, you know, very tentative or whatever you call it.
Yeah, I mean, I'm not like singing the praises of these big journals, you know, like Nature or anything.
I think they will eventually get eventually they will get moved by these journals once they prove their myth, you know.
Well, I don't know about that, but they're just so big, and they're it's expensive and all that.
Yeah, and also they are highly parochial, you know. I don't know if that's the right word, but parochial in the sense that it's quantum mechanics and the general relativity. Somehow you have to ascribe to that. If it's not, if it's something new, that they're, you know, sometimes they outright reject that.
So, well, I suppose if you're going like against, let's say you go against general relativity, and then they might decide, well, we'll just reject that because we have so much experimental evidence that it's true. And I think if they're of that opinion, they do have that amount of evidence, then in a way I'm kind of all right with that, you know. But I think, so for a long time I was a bit hesitant on the issue of general relativity, like to fall on one side of it until I fully understood. I already understood relativity, but it was like other things, other information that seemed to conflict with it, and so it took a while for all of that to work out, and now and I don't think that you were trying to disprove relativity, but
no,
you seem to be bringing in superluminal things. Yeah, and that would be one issue I would have with your work. Not this stuff that you're showing, but I think a couple of weeks back you had like a wave or something, and then there was some noise in the wave or something. So I assume it's connected to some of the things you showed here, but I'm not sure. But just for me personally, like, it's like, well, where is this superluminal wave? You know, like it's obviously in this other dimension or whatever. So how are you getting any data? So then all of your data is synthesized, isn't it? It has to be just created.
Actually, in a way, because you see the background noise. If you can pick up the background noise, the background noise may be the superluminal thing. That's my feeling. Like it's an experiment, right? I think I said an experiment of a pendulum isolated in a chamber with no interaction with the environment.
But I mean, why would it be that? Why would it be that though, and not just noise?
No, so it is staying there. Underneath there is a noise, superluminal noise, right? But this noise, what happens is over a period like a decade or something, the noise has, like I said, a gradation. So you have a tensor making it a vector, and eventually it will have, and I have proved, I think mathematically I have some proof that it will start oscillating. You know, it will start oscillating.
Yeah, I don't understand that though, like, because I mean, I don't know. I would want to see like some very rational proofs of why that would be the case. But I'm just like, I need, I need stuff like that. And if I'm talking to the person who's, there might be like some experiments that are done that I don't fully understand, but maybe the person who did them has long since passed away or something. But since you're here, I would expect like a full explanation of why this experiment, what you think.
It's actually with Lagrange, like you said, Lagrange, how the Lagrange changes with with these our new concepts. The Lagrange is one of the answers. Of course, Lagrange and Hamiltonian are related. Lagrange is the general relativity, and the Hamiltonian is the quantum mechanics. They're related by Legendre transform. So you can convert one to another.
It's also the case that the Hamiltonian is like L or T equals U plus V, whereas the Lagrangian is T equals U minus V or something.
Yeah, I mean the kinetic minus the potential.
Is it there's a plus and a minus change? Yeah.
Yeah. Change. So it's a differential of the how much the kinetic energy is over the potential energy. That's what Lagrange is trying to figure out.
Right. So, and then you can use those how do you say
Legendre?
Legendre transforms.
Yeah.
To do that.
To convert one to another, Hamiltonian into into Lagrangian, Lagrangian into Hamiltonian. But I'm sure people have done this. I'm not sure. I've not seen people using explicitly. But I wonder why they didn't. They should convert to one unit. That's why I use Legendre. Legendre itself is the best way and transform, because you convert Hamiltonian into Legendre, and so that means quantum mechanics into Legendre form, and the general relativity from Lagrange into Legendre form. Then you are comparing. You are not comparing apples and oranges. You are comparing the same thing. People have not done that. I have not seen anybody doing with the Legendre, where both of them come together in the same type of transform. So you can compare them, and then I've not actually done that. How easy it is to do that, because Einstein general relativity, highly complex thing, very composed very compact equation, right? How you can convert them into Legendre is very challenging. The same way Schrodinger thing, the original Schrodinger thing, again, I think is a challenging thing. So I don't know whether we have to make assumption. People have done numerical relativity, things like that, to solve the problem. In the same way for, I believe that even Schrodinger, you can use the numerical method. Or what I have done is, for vacuum is same as a diffusion equation. So if you're solving for vacuum, I think both of them, you have to use Legendre and vacuum, probably. So then all of them come together. So I think I'm sure you may get a different vacuum energy. That's the problem, right? Vacuum catastrophe. But you convert this and then solve in the vacuum, whereas the Schrodinger equation becomes like a diffusion equation, error function equation. And then the general relativity in the vacuum sense, you convert a Legendre into Legendre. Then again, what happens to the energy tensor and everything, the G mu nu, everything, how does it convert? So if you use that, you may not have this much disparity with the vacuum energy. I somehow, I'm not sure, when you calculate only, but somehow in the back of mind, I think you may not have that much disparity. It's because of the difference in the way your transform is. You're comparing apples and oranges in some sense, in that sense. So I think that's worthwhile. It's not an easy thing, and that's the problem. It's not very easy. The math is highly involved. Like I'm doing the case 3, right, for Emory. When I go to case 2, it's not that I manipulate a few codes. I get that. No, I have to work a lot. So it may be totally different. Am I not getting that same thing? So again, the codes, I believe in codes. Eventually, like you are doing IT code, we have to do physics. I call physics coding. We may have to do that eventually.
Yeah,
I think that's the solution to the problem, because then we can manipulate things, we can simulate things.
Absolutely, yeah. I think this whole thing about just equations, and I think it's the wrong way to go at this stage.
Yeah, I think it's more like physics coding you have to do.
One thing to do everything implicitly, kind of like with nice, clever equations. But if we have a computer that can just do it all out explicitly, why not just make use of that? And you should be thinking. Not you, I mean, but like the scientific community,
in general,
physicists should be thinking about how to apply their ideas in this way and actually do things out explicitly.
Yeah.
And if they can't do that, then come up with an idea that you can do that with, and then that is where you will start finding answers.
Yeah. The math simulation with the coding, physics coding, will be the best way. Because then you have at least a mathematical way. Even string theory, you have mathematical way of simulating that, and then you can come up with parameters. The parameters automatically, I think, will come in that coding or the program. The parameters will start appearing, and you just have to interpret those parameters, and then you get a way to do the experimental, verification. I think it'll pop out of that. Use a very high level artificial intelligence or something, and it'll automatically pop it out using similar, because it has to compare similar thing, categorization and all that, and the AI can do all those job.
Yeah, I'm glad that you're thinking that way. I think that's the right approach.
Yeah,
for sure. So what are you looking at here, Raja?
Yeah.
You've got a 2024 agenda, time, quantum tensor, matrix entity.
Yeah. So this is what I think the final thing the universe is. They are either part of matrix, entity, vacuum, or quantum. I'll give you a list of that.
I'm not sure what that means, but continue.
Yeah. I mean, it's kind of a new thing. Again, I had to really write it out. But this is where I'm going with that. I talked about At some point, maybe I will play that the movie.
You don't really want to go into that here, is it? Yeah, that's more. That's more further on down the thing.
So now let me tell you what this matrix is. The entity could be particles, quarks, matter, the phonons. I didn't write photons, brain. The matrix is simply space, sense. Then you have the kind of entanglement, fields. Fields are part of that. Environment is part of that matrix. Then vacuum is neither entity or matrix. It's not entity, not matrix. Is the vacuum. That's zero potential, like a flat brain. Then Conda has all these things together: energy, entity, our life. Humans are in this. So the whole list. This is part of the list, but you can so this list includes all that. I think these four will categorize everything that's in the universe. And then based on that, we can come up with the algorithm. Again, in the same line, I'm thinking about the physics code, the math simulation with the physics coding is the ultimate answer to come. So but you need to input these things. The computer needs this, and then convert this into some kind of algorithm, and then you put a list, and then recognize the list, and somehow the artificial intelligence will start analyzing that. I'm hoping.
Oh, okay, yeah. Yeah. That sounds like something that needs to be.
Yeah, there's a lot of work to be done to do that. Maybe you can work together because you are more of IT. You have expertise in that regime.
Right. I would need to know exactly what you're going to do with.
Yeah. So I'll try to write it out. Yeah, I'll try to write it out and probably get peer published.
Yeah. Well, I look at the superconductivity thing that you're working on at the moment. Sounds like the most promising, but you need to get it. You need to get it peer reviewed to make sure it's correct. Because I can't do that for you, but it's just something about it strikes me as how do you say it? Like it's got potential. It sounds like it has potential.
Yeah. So because I want to run by you because you will know that, and thank you for your
Oh, no problem.
For your input, because that helps me. I have so many things where I should immediately concentrate because these journals are coming after me. Why didn't you send it? Why didn't you send it? But I am kind of in a quandary, so to say, which one I should send it. So, but now you are clarified. Maybe I will send this the vacuum thing and the superconductivity thing, right? That will be my priority. And then I will send to.
I'll send that too. Sure. Yeah. I mean, do write that up, and then say it sounds like the best one. Sounds really interesting. So, and I would send it on to a paper that has like really reputable reviewers working for it. Yeah. And that'd be great then, because they could get back to you and say, well, or they could give you like a positive or a negative, and then whether you're on the right track or what you need to change to make it better. That could be very useful for you.
Yes.
Instead of maybe working with, I know these other journals are great because they kind of do publish your work, which is good. Yeah. Gets it out there. But if they're not going to be really critical of your work, then you're not going to improve, and that's not going to be good. So I'd try and send it to like one of the big journals and get them to really criticize it, and because if it's good, then it will be published.
See, one of the things is that I'm circumspective. I don't know if it's the right word. Circumspective of big journals is that I don't say they cheat or anything, but really good work. Sometimes they'll say it's not good, but they'll change a little bit and then so you cannot claim it, but essentially your idea is what they're using. So I don't know whether they do that.
I didn't know that. You're saying that some of these
I think I have reason to doubt that, because I find my idea was the original one that was years ago, and later on I find, but of course, it was refurbished. So you cannot claim it.
Oh yeah, they have broken it. Things like that are going on all the time, but yeah. Well, yeah, I wouldn't worry about that though, Rajan. Just
So what I want to do is publish one of these.
It probably doesn't happen all the time, but I know of cases where, for instance, there was a French guy who was talking about dark matter and voids in the universe, and he was saying that, well, maybe the dark matter creates these voids, and I think maybe he was talking about dark energy as well, creates the clusters, and then no one really listened to him, no one picked up on his work. I don't think he was allowed to publish it or anything. And then years later, some woman working in came up with pretty much the same concept, and she was considered great. She gets a Wikipedia article about her, and it's like, hang on a sec, I heard a French guy 10 years ago talking about this, but a kind of similar idea, but that's the only example I can think of. But and I wouldn't even say that could be just a total coincidence. Like, what I think is, like, if the scientific community, they all have a consensus and they're working around that consensus, and there might be somebody outside the consensus with a slightly different idea, like a unique point of view, and they'll just ignore this person's idea. And then, but if over time experiments and observations prove the consensus wrong, then they will start to like look for other ideas. And one of those potential ideas might have been this guy's, but because he's like long since vanished out of everyone's attention, someone goes, oh, why don't we just do this? And it just happens to be like in the same area as what that person was talking about 15 years before, but now it's just like fashionable, or because of the new data, they're allowed to talk about it. So that, I think, is interesting, and kind of a bit annoying as well, that there's a consensus, but we also need maybe a plurality of voices, so that when the consensus is eventually broken, which it has been multiple times, that then you can then examine these different things. But also, it's worth pointing out that if let's say in the case of the Big Bang, for example, and they're finding out that the universe, the age doesn't match what they're observing. Okay, well, that seems to then disprove the model, the current age of the universe. But they cannot then. So an option is then to make the universe older than it first appears. But that doesn't mean they can like move towards some other previous alternative options, such as like the steady state universe or something like that, because it doesn't fit with certain other observations, or the steady state universe was disproven for other reasons. So once you keep all those ducks in a row, and it's got to be a Big Bang universe of some sort. It's got to have redshifts, and it has to be certain age. Once you have those kind of things involved, and you can explain the strange observances of the galaxies that are so much older than they should be, then you're okay. Then your theory should be publishable. But whether it will be or not is another story. I think you'd want to get lucky. You'd want to probably send it over and over again, refine it, and get a good reviewer who's like open-minded enough and is like smart enough to know that there is a problem, or honest enough to know that there is a problem, and smart enough to know that what you're proposing solves that problem. But I'm not talking from experience here, because I haven't sent any of that kind of very controversial or groundbreaking work at the moment. I was reading something in the corner of my screen, so I shouldn't say groundbreaking, because I haven't broken any ground yet. I haven't sent it to the journals, but you know what I mean. Like, it's controversial work. Like, I haven't gotten any feedback from them on that, whether they just pan it because it's slightly different to what's going on, or whether they recognize, oh well, here's actually an alternative explanation that could actually explain some of the things we're seeing, and therefore we'll give it a go. I'm not gonna, since I don't have the info on, I don't have a crystal ball to say what they would do, and there is no they either, because it's just a bunch of random people that are selected randomly to review your article, you know. So there's no they, and there's, you know, we don't know what the future will hold. So as long as your work is up to scratch and you're lucky enough to get someone who's interested in it, then that's good. But if it's stopped at the start by like the editorial team or something, that's where I have an issue. Is the idea that like there's this one person who's in control, like the gatekeeper of all scientific knowledge, and it's just like the editor of the journal, and they take one look at your paper and they go, no, I'm not going to publish that because I don't like it, because it goes against my research. And then they get the assistant editor to just agree with them because otherwise they'll be fired or whatever. That's not good. I think it should be just given to the, because then there is a they. There's a prick on the top. He's just controlling everything. That's not good. But if it's a review system and it's honest and open, then, you know, you should never, I would not contest that. I mean, obviously you can contest individual reviewers, but if you have two different reviewers from different parts of the planet who don't even know each other, and that's important. They have to not know each other, and they have to not know you as well. And if they both disagree with your work, then there's a good chance that your work is wrong. You know, but if one of them agrees with you and the other one doesn't, but you're able to point out why that person is wrong, then you were right, and your paper should be published. And I think that's generally how it should work. And I believe that is, well, I was listening to a lecture by people who work at MDPI, that paper, and they say they operate like that. So I'd send it to MDPI or MPDI or whatever it's called. Do you know that?
MDPI,
yeah. Send it to them, because they sound like they're trying anyway. I don't know what's going on behind the scenes there, but if they're doing, don't send it to like someone like Hindawi or something, because I found them not to be.
Medwin Publishers.
Medwin, is that who?
Medwin. MDPI is Medwin.
Right. Yeah, they sounded like they know what they're doing. So send it to them. Pick the journal.
Some of them I have published with them.
The
biophysics. So some of them are the Medwin Publishers. Two of them with the physical thing. Two of the magazines.
Send me on those. I'd be interested to read the ones you got published with.
Yeah, Medwin. And one of the things recently I have experienced, because I was reviewing a very high level paper in tensor physics, high level for the laser. Some people, they have written good this thing, very highly mathematically involved. So I was reviewing, and there were 3 reviewers, right? I don't know who the other people are. They just send me their comments. I don't know who they are, but they seem to be really expert in their field. And the reviewer too is very similar to mine. I'm surprised. I'm happy. It's not same, but in the same, along that similar line, we are not duplicating each other in the sense that he does not know my work, my review. I don't know his review, but so happened that we are looking at different points.
Right.
And he points. Then I say need a major revision. The first time I said, and he also mentioned major. The other person rejected it. The third one. And then again they sent to me, and then the authors did a fairly good job. So I said that it's publishable, but the second reviewer has said that you need a minor revision. And again, I have not seen his eventually I will get all the comments. They will send all the comments. But then the author has requested a third person to consider, because they changed everything. So that they didn't see, the problem is they didn't define certain things. I have a big problem with that, but I don't want to reject them. It's a good, it's a breakthrough.
Okay, that's good.
So I said that, you do define certain things. You are using these vector quantities. You are converting the vector quantity to something, or the tensor quantity to something. but there's something in between missing, the derivation. So then they added those things in between to clarify. Some foreign countries, they have difficulty with English, right? So, and also explaining a thing, but they are good in math. They're really good.
Well, math is a universal language.
Yeah.
So is English, though.
But the English, the communication, they don't explain very well. And I cannot say I am, any better. I'm not an English thing. I also have, weakness in that. But I think I have rectified to a large degree.
So, it doesn't have to be perfect, for...
Yeah.
Just as long as you get your point across.
Yeah. My thinking also changed.
Is way more important, isn't it, in science papers than... You shouldn't be explaining things in words anyway.
Yeah.
Okay, Rajan. I'm going to... do you want to leave it there? We're an hour and a half in.
Yeah. Sounds good. So we'll see you next week. I think in 2 weeks,